Welcome to my talk. This is work done in conjunction with a graduate student, Murray Bennett. Also some collaborators, Ami Idels, Mark Adam, Mark Stivers, and I'm Scott Brown. This work is about Dutch auctions and especially about developing a model for them. A Dutch auction is one that operates in the reverse to what many are used to. The price decreases and decreases until the first person makes a bid and then they get the item. This is a picture of a very early Dutch auction in Germany for some boat products. But the auction gets its name from these, which are tulips and other flowers for sale at a very famous flower market in the Netherlands, and they're sold by Dutch auction. The Dutch auction is very good for this kind of product because these are perishable and the Dutch auction operates quickly. The way it works for the flowers in the Netherlands is that the flowers go through on conveyor belts down the front, and as they move through, the price for the flowers decreases, and then the first person who presses the button to buy the flowers get them at whatever price they're currently up to. Another item that gets sold by Dutch auction are fish at the Sydney Fish Market at least. This is a picture of the Sydney Fish Market and you can see those clocks up at the top of the screen there. Every day the fishermen bring their catch in, the buyers sit around and they watch those clocks. The clocks count the price down, and then as soon as one of the bidders presses their button, they get the fish for whatever price is currently shown on the clock. Here's an example of it working in practice. This is the clock that's actually in the market, and here you can see the price going down and down and down until someone called Huang buys one of the remaining items. You can see there are 15 items in total, 7 remaining, now 6 because someone else has bought one at that price. And now there's another auction and it continues doing the same thing until someone buys another one. And this process goes on until all of the items are sold. The Dutch auction has lots of advantages. Particularly, it makes sure that things are sold quickly. There's an end point. The clock will stop at some point. It's also very good at maximizing throughput when there's lots of items that are the same to be sold, because there are different ways you can sell them such that they go in bundles. It's used a lot, not just in the perishable goods markets, but also in financial transactions. Quite often, initial public offerings of publicly listed companies on the share market are made by Dutch auction. Now, there are no really good detailed quantitative models of bidding behavior in a Dutch auction. And I think that maybe one of the reasons we're missing those models is that because there's also not really good detailed quantitative data about people's behavior in the Dutch auction. So in that paper I mentioned earlier, we together produced a lab-based Dutch auction where players came into the lab in small groups of 3, and they bid against each other using an interface that looked a bit like this. The bidding operated as much as we could, just like a real Dutch auction, where the price fell down and people saw their bids get beaten by others and saw their bids win. They had a certain amount of money to spend and repeated auctions on which to spend it, and they had to try to fill their warehouse. The game was set up in such a way that there was real competition. They couldn't all fill their warehouses given the resources available. Now we got really detailed data out of this, what people bid and precisely when, and even some information on what their opponents were doing. But what we didn't get, and what's common I guess in many lab experiments, is some ecological validity that would be provided by bidding for real things and paying real money. In sciencey terms, I guess our experiment was not incentivized, and there's quite a bit of research showing that incentivized experiments can sometimes lead to different outcomes than non-incentivized experiments. Actually making people spend their own money and have the chance to earn money can really change things. So if we really want to understand how Dutch auctions work and really test in detail a good model of those, we need some real data. So YouTube came to the rescue for some real world data. A few years ago in England, there was a home shopping channel called Price Drop TV, and it worked with a Dutch auction format. Presenters would appear in the middle of the night and they would sell things like this fabulous diamond ring, and they would have 10 of these for sale in this case. And you can see the price there, £1,453. And then the price would slowly decrease the longer they talked, and it would keep decreasing until people started buying the rings. And then that Dutch auction process would continue on and on until either the last ring is sold, so the quantity left goes to 0, or they reach some floor price, a reserve, at which they don't want to sell anymore. Here you can see a different auction. This one is for a delightful amethyst 3-row bracelet. If you watch the pulsing purple triangle, you can see the price decreasing. This is the Dutch auction clock. And if you watch that yellow triangle that says quantity left, you can see it's 7 now, but then as people ring in to buy these things, the quantity starts dropping. There's one gone now to 6 and another to 5. So the quantity goes down as the price goes down until the auction's all over and they hit their reserve or run out. Just there, they hit the reserve price and ended the auction. So I asked an unfortunate undergraduate research student to go a little bit mad and watch hours and hours of YouTube price drop TV and record everything that happened so that we could have some real data on the Dutch auctions in real life. This is the sort of Dutch auction data they record from that. You can see that there's information about what's being sold, how many of them are for sale, when the auction starts and finishes, what prices it starts and finishes. But then this is the detailed line by line data where it shows at what moment each person rang in to bid for one of the items. So you get for every bid, the time it was made, the price that the person was willing to pay on that bid. I'll use those line by line data that you see now as the example in the rest of this talk. They're about an auction where 150 pairs of binoculars were sold on Price Drop TV, and they started selling at about £7.49, and by the end of it they were selling much, much cheaper than that. We started our modelling efforts by looking at the data from the lab experiment in this paper, the one that I talked about before. Now remember, in this experiment people bid against 2 others in a lab-based Dutch auction. Instead of trying to directly model the price people were willing to pay or how long that they would wait before they made their bid, the way we approached the modeling problem was to think about it as if there was a repeated sequence of decisions. At several moments repeated during the auction, people would decide between bidding now or waiting a little while and then re-evaluating the decision. At each one of these moments, then you've got the safe option. The safe option is to buy right now because you'll get the item for sure. Sure cost, sure benefit, known price. And the risky option is to wait a moment. It's risky because if you wait a moment, one of the other players might beat you to it. They might bid and purchase the item while you're still thinking about whether to bid again. We set up the decision making using prospect theory. We just use some fixed parameters for this based on historical literature. The way it works is then you have a cycle like the one on screen here, where at each moment prospect theory chooses between buying now or waiting a bit. If you buy now, you've got a 100% chance of getting the item. You've got a known loss, that's the money you have to pay, but also a known gain, the item that you will win. If you wait a bit, there is some chance that you'll miss out. So there's a probability that you'll miss out on the item completely, and there's no gain or loss. So then you wait some fixed amount of time. In our model, we always have the same amount of time for every wait, and then you reevaluate the decision with another round of prospect theory. Now, what this framework gives us is sort of a framework on which to build the interesting psychology of the model. So we can ask, how do people guess the chance that they will lose the item if they wait? So maybe they have something like this in mind, an internal model of when the other 2 players in the lab game are going to bid. And then they can use that to guess the probability of losing the item during the waiting period. With all these bits in place, the model makes predictions like the ones you see here. It predicts the time at which you're likely to bid, and it also predicts changes in that time depending on psychological things. For example, this picture shows us how the predicted bidding times would change if the person has in mind an earlier idea about when one of their opponents might bid compared to before. You can also change things not about the other bidders, but about the item itself. So this picture shows how the predicted bidding times will change depending on the subjective valuation that you have for the item being sold. You know, if you think it's a really great item, you're willing to bid earlier, and if you think it's a poor item, you'll hold your bids till later when it's cheaper. And this model gives quantitative predictions for how that will happen. We built on the lab model to develop a model for the real data from Price Drop TV. Now, do you remember the Price Drop TV data that I'm going to use in this talk are the ones from the binocular sale? That's these data that are on screen now, where 150 pairs of binoculars were sold at varying prices from about £8 down to about £3. Now, just before we get started on this, let me remind you the prospects that were involved in the prospect theory model for the lab-based data. In the lab-based data, the prospects were between a sure thing, bidding now, where you're guaranteed to get the item, versus a risky prospect, where you can wait for a little while and you might get the item, but you also might lose it if one of the other two bidders jumps in while you're waiting. The prospects in the TV version of this are slightly different. They're different in two ways. One thing that's different is that when you decide to buy the item, you don't get it immediately. You have to call in and buy it. And that takes some time, and there's a small amount of chance that you'll actually lose the item while you're ringing in. Now, the chance of losing the item is not quite as simple as before because there's many items for sale, 150 binoculars in this case. And so you'll only lose your chance to buy the item if all of the remaining items are sold before you get your turn. The other way in which the TV version is different is you're not just bidding against two people, but a very large number, the entire audience. This means that you can't make your guesses about the probability of being beaten by just thinking about the probability distribution of two other people's guesses. So instead what we do is we have some group version of this. The picture on screen is meant to indicate that. It shows some distribution for the times at which you think the entire audience make their bids. Now, once you've got that distribution, you can estimate, as a watcher or as a decision maker, you can estimate the probabilities involved in the prospects. The probabilities are given by the chance of items selling out before you make your next decision, plus the chance of the item selling out while you're still on the phone waiting to get through. That's the green bar. So the prospects in the TV version of the model are defined by the usual prospect theory equations with their fixed parameters, but also the probability P of losing out on the item before your next go, the gain or loss X, and the sensitivity C. The probability P is something that we can work out in the way I just described by having an estimate of the audience's bidding times and looking at the chances of people bidding out all the remaining items before your next decision and before you get through on the phone. The gain or loss is defined, like always, by the loss that you'll have to pay as a price for the item and the gain, which is your subjective valuation of the goods you're going to buy. You know, how much you love that amethyst band or the binoculars. There's one more parameter in the model, which is the sensitivity C, which is something that determines the randomness versus determinism of choice making. It's just the temperature of a loose choice rule, which is added on to the end of the prospect theory outputs. With all this in place, the model makes predictions like these. On the left panel, you can see the price of the binoculars decreasing from £8 down to about £3 over the course of the auction. And you can see it goes in little steps here and there. That's part of the sales process. The presenters change things when they think it needs to be changed and hold it steady when they think it's not required. The number of binoculars remaining is in the middle panel, and that shows the times at which people bought in and took some of the binoculars out. The third panel with the red histogram shows the model predictions. That's the density of bids given the prices and the parameters of the model. So what we've got now is a working model that produces predictions which roughly match the data. What's left to do are to gather more data from YouTube, as long as my undergraduate research helper doesn't go completely mad, to develop estimation methods so that we can properly estimate the model across many participants and many different auctions, and then to get to the interesting bit, which is to build on the psychological complexities that are interesting, to work out what the model predicts about when you misestimate others' valuations of the binoculars, or when you misestimate probabilities in the way that we know people do, or what happens when the presenters of the Price Drop TV use their sales techniques to try and encourage more sales by rapidly dropping the price, holding it steady, using other things on screen like graphics and so on. We can enter these into the model in different ways and see what effect they have. That's all I've got time for today. Thanks very much for listening, and thanks very much to all my collaborators on this who are listed at the bottom.